Okay, we got fall 2017 Chem 115 final, so let's jump into it. Question 1. Which one of the following series of radioactive decays would convert that element, mass number 234, into radium-226? First of all, let's figure out what the atomic numbers of these elements are. So we had Pa, which is 91, and then we had radium, which is 88. So let me write that in there. This one was 91, and this one is 88. That'll probably be useful to know. Okay. So, let's see here. We're probably going to have to go through and brute force check this, but I think we can quickly eliminate some of the choices because, let's see, if we write what our particles are, beta minus is 0 and then -1. A positron is 0, 1, and then an alpha particle is mass number 4, atomic number 2. Of these three choices, because these are the only ones present in these choices, of these choices, the alpha particle is the only one that's going to change my mass number. And I can see that we're going to need to decrease mass number by 8. So we're going to need to go through alpha decay at least twice. Well, not at least twice. We're going to need to go through alpha decay twice. So A is not true, and only E is not true. Because I know we're going to have to go through alpha decay twice to get to the right mass number. Now we just got to figure out the right series that will get us to the right atomic number. Now it's worth noting, actually, we don't actually need to check the processes because it doesn't matter the order we apply these in. So let's just figure out how many beta minus particles we need to apply. So essentially when we apply the, let's take our initial example, 234, 91, and that's Pa, and we're going through alpha decay twice. So I'm just going to write out this example. And then we will have 230 and 89. I don't care about what element that is. I'm just going to leave that blank. And if we go through alpha decay again, it's a 4. It's a really bad 4. Anyways, if we go to alpha decay again, we're going to have 226 and 87. Now, the only problem with this is that our atomic number is 1 less, so we will need to go through, so we're at, I'm like starting on the next line so I have more room. We need to make this into, through some form of decay, we're going to need to make this into 226 and 88. So in order to do that, we're going to need a beta minus particle, right? Because this is the balanced equation. I know, 88 minus 1 is going to give me the 87. So that leaves us with 2 alphas, or 2 alpha decays and 1 beta minus decay, which is only D. Only D has that option. Okay. 2. Which one of the following nuclear processes will produce xenon-130? Let's find xenon. It's a noble gas. It is atomic number 54. Let's just go through and check all these choices, unless they're maybe completely ridiculous. Then we can eliminate them. Okay. Well, here's our first choice. It's iodide, and they're proposing positron emission. So iodide, 130, 53. Okay, hold on. This is a mess. We're going to need to go a little bit smaller. Okay. Iodide is mass number 130, atomic number 53, and they are suggesting positron emission, which is 0, 1. And if we balance this, we have this element, which is, what is that? Te. Whatever, we get Te, whatever element that is. And that Te is not xenon, so it's not A. I'll leave that up there. Okay, gamma decay of xenon 131. Gamma particles have mass number and atomic number 0. So it actually wouldn't change our mass number. Therefore, I know B is not true. I'm not going to write out that one. Because I just know the gamma particle is not going to change anything. At least with respect to mass number and atomic number. Okay, beta decay of iodine 129. I'll go back to orange. Iodide, mass number 129, atomic number 53, and they are saying beta decay, 0, -1. And if we balance this, I'm going to get 129 and 54, which is xenon, but the mass number is wrong. It's not C. Let's try D, electron capture of cesium-130. Cesium is right there, it's group 1. Okay, if we write this equation, we're going to have, yeah, we'll do green. Cesium, mass number 130, atomic number 55, and electron capture is this. So you will get 130 and 54 of xenon. Okay, my handwriting's really bad, but you get the gist. And that's mass number 130, and that's xenon, because xenon is atomic number 54. 2D. 3, half-life problem. Let me fix my markers. Okay, half-life problem. Cobalt, mass number 56, has a half-life of 78 days, starting with 1.42 milligrams of this isotope. How much remains after 312 days? Okay, I don't know. I'm pulling out the equation sheets, which I printed out, because you will be given these on the test, or at least you were in 2017. Don't quote me on that. Anyways, the half-life equations that we care about. So the half-life is equal to the natural log of 2 over K, as well as KT equals the natural log of the initial amount over the final amount. So we're going to use these. Generally, we're going to use a system of these two equations to solve for one ending variable. They want to know how much remains after 312 days, which is going to be our final amount, which means we're probably going to have to solve this one first. So, yeah, we're going to need to solve this one first to get our K, and then we're going to plug K in right there to solve the second equation. So, let's solve one first. We know the half-life is 78 days, and that is equal to the natural log of 2 over K. I don't have a calculator. Oh, my calculator's low battery. Okay, anyways, 78, or we're going to do natural log of 2 divided by 78, and that is my K. So K equals 0.00889 inverse days. Okay, so now we can move on to equation 2. Let's just plug it in. 0.08, wait, there's another 0. 0.889. I'll keep units going. Inverse, actually, I'm going to omit units. Yeah. Inverse days equals the natural log of, let's see, the initial amount, which is 1.42 milligrams, over, okay, oh, oops, I forgot T. So they want to know how much after 312 days. I omitted the units, but this first number is inverse days, and this is days. So inverse days times days is unitless. And we're solving for n naught, or we're solving, sorry, n. We're solving for n. Okay, one equation, one unknown. So I'm going to take that 0.00089, and I'm going to multiply it by 312. And then if I were to simplify this, so when I do this multiplication, I got 2.773, and that equals 1.42 over n. I did just do 2 steps there at once. I multiplied these two together, and that's what this number was. And then I took the exponential of both sides to get rid of the natural log. Now, if I take the exponential of that number, I get about 16, and I can do 1.42 divided by 16. If you solve this algebraically, you will get n equals 0.089 9 milligrams. I know it's milligrams because that was the units of the other one. 3C. Problem 4. Which one of the following statements is true about nuclear fission? A, the mass of the product is greater than the... Okay, so all of these products, or all these answer choices are talking about mass changes from fission. There is a problem similar to this in one of the other exams, but actually I'm not going to know this. I'm not going to write that. So what is fission, first of all? It's like the splitting into like a big particle into smaller particles. And the reason it does this is because this state of the smaller particles is lower in energy than the big state. It's a more stable conformation. So as we undergo this process, we decrease our energy, and that's why as we lower the energy of our molecules, a ton of energy, all like the difference in energy is released. That's why it's such like an exothermic process, how like nuclear bombs and stuff work, because a ton of energy is released because we're going into this lower energy state. And we know that energy and mass are related through this relationship, E equals mc squared. So if you undergo a process like this where you're lowering your energy, you also have to lower your mass because the speed of light is not changing. It's a constant. So the mass of the products is greater. That's not true. A is not true. The mass of the products is less. That's the right answer choice. The mass of the product is the same. That's not true. That is not consistent with B. And then D is the mass of the product is 100 times greater. We have no idea if it's 100 times greater or not. We don't have any specific numbers. So we're going to go with 4B. Nice. 5. In visible spec, the wavelength of maximum absorbance is usually used for spectrophotometric analysis because... I feel like I answered this exact question. Anyways, so this is a Beer's law problem. And Beer's law is the absorbance when we shine light through a species is equal to the molar absorptivity, which is a property of the material, and then the length, and then the concentration. And when I say length, so imagine, yeah, actually that's fine. Okay, so imagine I have a beaker, and I might want to measure the concentration of my sample at any given time. So I have some sample of this green stuff. I want to measure the concentration. One of the easiest mechanisms to find the concentration is by shining a light through it and seeing how much comes out the other end. Also, essentially just looking at the absorbance in the solution. Because if whatever species I'm looking for the concentration of in the solution absorbs that light, I can correlate concentration and absorbance through that law. Now, you're going to use this to measure changes in concentration, and so you're going to want your absorbance to be as reactive to changes in concentrations as possible. So your species, we have this player. Let me draw this plot. We have different species, and if I plot absorbance versus wavelength, we know different materials and molecules are going to absorb different wavelengths more so. So that's why some things might have color, right? Is because they're reflecting the color you see, and then they're absorbing a very high amount of the other wavelength and color of light. So for a given species, I might have a curve that looks like this, where at this wavelength, it absorbs a ton of the light. We're going to want to use this maximum wavelength. Shoot. I'm trying to draw a lambda. Well, okay, why am I not? Anyways, we're going to want to use that maximum wavelength that it's going to absorb the most, because per change then in concentration, we're going to get very big changes in absorbance, which means they're going to be easier to measure. So on our like lab equipment, if we have greater changes in absorbance, it's going to be able to increase our precision for measuring concentration. So let's see what answer choice that lines up with. The change in absorbance per unit change in concentration. Yeah, okay, it's A. Right, because we want the biggest absorbance change per unit, per change in concentration. Because if it was really small, if we could change if it was the opposite of what A is saying, if we could change concentration and not really observe much of a change in absorbance, we wouldn't be able to, we wouldn't be able to really observe the concentration. Like we want concentration to be as strong a function of absorbance as possible. So we want answer choice A. B is the opposite, so that's not true. C is not true. The spectrum sort of looks like this, where you can absorb in multiple regions. D, chemical substances absorb visible light equally well at all wavelengths. That's not true. That would kind of imply everything's the exact same color, which, obviously is, that's not true. So we're going to go with 5A. 6. A modern compact fluorescent lamp contains that amount of mercury. If each mercury atom in the lamp were to emit a single photon of that wavelength, calculate the amount of energy that will be emitted. Okay, so we're given a mass, which is really just a way of finding out how many atoms we have, and we know a wavelength, and they want energy. Okay, so let's look at our equation sheet. I know that energy of a photon is equal to Planck's constant times the frequency, which is equivalent to Planck's constant times the speed of light, which is also a constant over the wavelength. So I know a wavelength, and I know h equals 6.626 times 10 to the negative 34th, and c equals 3.0 times 10 to the 8th. I might want to fact check those, actually. Those just came off the dome. Okay, they're not on my sheet. I'm just going to assume they're right. Anyways, let's keep going. So then my energy, and this is the energy of one photon. Okay, so important distinction there. Let's just start plugging stuff in. 6.626 times 10 to the negative 34th times 3.0 times 10 to the 8th over the wavelength that they give us. Now, important distinction here. Speed of light is in meters per second, and the wavelength they give us is in nanometers. So 254 nanometers is going to be equal to 254 times 10 to the negative 9th meters. We're going to want these meters to be in the same unit, so they cancel. So let's find my calculator, and let's throw that into the denominator. Okay. All right. Let's chuck this into the old TI-84. 6.626 times 10 to the negative 34th times 3 times 10 to the 8th divided by 254 times 10 to the negative 9th. All right, so the energy of one photon is going to be equal to 7.83 times 10 to the negative 19. Okay, now that's of one photon. Our species we're trying to analyze is not one photon, it's 1.4 grams. So this is essentially the energy of one photon, or one atom, sorry. Okay, because each atom's emitting one okay, this is getting messy, geez. One atom is emitting one photon, so I can just go from one photon, like I'm changing my one photon into one atom. Anyways, and let's find out how many atoms we're going to have in one atom. We have a, wait, hold on. Let's go to moles. We're going to need to go, okay, in one, shoot, wrong color. I know there is an Avogadro's number of atoms in 1 mole, and then we can go from mole to milligrams, and then just times out milligrams. So 1 mole, and then we're going to need the molecular weight of mercury. All right, let's find mercury on the periodic table. 200.6. Also, I know everything I just did. I went through pretty quick. So I want to find the energy of my whole sample. So therefore, I'm going to want the energy on a gram basis. What I'm doing right now is I'm converting this from a energy on a atom basis into a per gram basis. So when I do this calculation, I'm going to get, also this is joules. I'm going to get joules per gram, and then I'm just going to be able to multiply in how many grams I have in order to get the joules. So let's solve this. 7.8 times Avogadro's number, which is 6.002 times 10 to the 23rd, and then divided by 200.6. Let's also put this in milligrams real quick, because they give us this in milligrams. So there are, in 1 gram, there are 1,000 milligrams. Okay, so let's also divide it by 1,000. And I get 2.35 joules per milligram. If I don't want this on a per milligram basis, I can just times by the amount of milligrams in my sample. Milligrams cancel, and I get, so if I take that last answer and times it by 1.4, I'm going to get 3.3-ish joules. 6b. Problem 7. The number of distinct emission spectral lines that originate from electron transitions between the first 3 energy levels in a hydrogen atom is. Okay. So let's consider, I'll give a quick conceptual explanation here. So let's consider like our like Bohr model of the atom. We have the proton nucleus, and then we have sort of these energy levels of electrons flying around. Now, we know they are attracted, we know our electrons have a negative charge, and so there's an attraction force here. And so the electrons want to be as close to the nucleus as possible. So the electron I just drew is in a lower energy state than the one I just drew that will be out here in the, say, 3rd energy level. So that first energy level electron is going to be in a lower state than the 3rd energy electron. Now, let's go over our diagram here. What I just drew is maybe an electron in the 3rd state and one in the 1st state. Now, there is this energy difference between the two. There's this energy gap. So, if an electron were to jump down to the 1st energy level, we know energy is always conserved in the universe, so this difference in energy has to go somewhere. And it goes in the form of a photon leaving with that difference in energy. And we know that the energy of a photon is equal to, some constants over the wavelength. So this photon that will be emitted from this exact difference, it will have a very distinct energy, and that very distinct energy will have a distinct wavelength. So that's what gives us the distinct spectral lines. It's because from energy jumps we get very specific wavelength photons. Anyways, that's sort of what's going on here conceptually. Let's see how we actually solve this. So they want to know the number of spectral lines that originate from transitions between the first 3 energy levels. So let's just look at all the different possible combinations. We have an electron go from the 3rd to the 2nd. Could also go from the 3rd to the 1st. Let's see here. Okay. And it also could go from the 2nd to the 1st. Sorry, I'm trying to pull something on my computer. Which leaves us with 7b. Sorry, I was pulling up the answer key. Okay. 8. Which one of the following correctly lists the 5 atoms in increasing size? Okay, so we know, I got the periodic table over here. We know size is generally going to increase this way. That's our general trend. And it's mainly a function of how far down you are on the periodic table, because as you go down, you add on energy levels. So in the first row, a hydrogen atom might only have 1 energy level. This hydrogen atom might only have 1 energy level, but lithium might have 2. So as you keep going down, you're going to get a lot bigger atoms. And then the elements on the left-hand side, as compared to the right, These ones are a little bit less electronegative, which means their energy levels are a little more relaxed, so they might be spread out a little bit more. So that's our trend in size. It trends this way, as in increasing size is in the bottom left. All right, so if we want to actually answer this question now, let's find all our elements and then just see which ones we can like list them in the trend we just saw. So anyways, fluorine is right there, potassium, germanium, I do not know. Oh, there it is. Okay. What else do we got? Bromine, and then rubidium, where is rubidium? Right there. Okay. So once again, the trend is this way, is like it trends with increasing size that way. So therefore, if they want increasing size, I knew rubidium's the biggest. So it's not E. And then the next biggest is going to be potassium, right? Because potassium's to the left more than germanium and bromine. So it would be potassium, and then germanium, and then bromine, and then fluorine, which is consistent with answer choice D. 8D. 9. Which one of the following correctly lists the 5 atoms in order of decreasing first ionization energy? So, first ionization energy is the energy it takes to remove the outermost electron. And it trends exactly the same, or very similar, it trends very similarly to electronegativity. I'm just going to call that ENEG, which we know electronegativity increases on our periodic table that way, with fluorine being one of the most electronegative atoms. So let's once again solve this in a similar way to the last one. Let's just find all our elements and see which one sort of follows that trend, and we can line them up. So anyways, chlorine, sulfur, aluminum, argon, there we go. Okay, and then silicon. Okay. So we know the first ionization energy, it increases in that direction of that arrow. Therefore, argon is the most, and then it would just be chlorine, sulfur. So I'm just reading right to left. Silicon, aluminum, which leaves us with answer choice B, 9B. 10. Which one of the following is the correct electron configuration for the manganese 2+ ion? So manganese is right here. And let's see here. If we let the answer choices guide our strategy a little bit, I know they want it in noble gas configuration. So I'm really just going to be concerned with the outermost electron level. So a ground state manganese would be, let's see here, argon. Argon is this atom. A ground state manganese would be everything after the argon configuration. So the argon is sort of accounting for the electrons in all of that. Now we just need to add on these, which is the 4s group. And then we need to add on these 5 electrons, which would be 3d5. Now we want the manganese 2+ ion, so if it's 2+, that means it lost 2 electrons. So I'm just going to take out the actually it's going to lose the 4s electrons first. So it will be 3d5. We're going to lose the outer energy level most electrons first. So that leaves me with answer choice B. And if I want to go over real quickly how I came up with this original configuration, I kind of just know it from memory. This is the first energy level. This is the S block. This is the S block. So those two I just circled, that's 1s. These are 2s. This is 2p. This is 3s. This is 3p. And then you get into 4s. And then D is a little weird in the sense that the energy level that the D is in is offset by 1. So P follows in the sense that this is like 4s and this is 4p. It equals the group you're in, but D is n minus 1, so this would be 3D. Anyways, also there's a whole video on electron configuration if that is not clear. All right. Problem 11. Using the information given below, calculate the heat released when 25 grams of N2O decompose according to the following equation. So first of all, we're going to need to find the delta H of reaction of this equation using Hess's law. So let's go ahead and start with that. They give us data on these two equations. I'll call them 1 and 2. And we're going to need to combine 1 and 2 in order to get sort of the overall equation. So the first thing I notice is that N2O only shows up in equation 2, and we want 2 of them on the reactant side. So I'm going to take my second equation here, flip it, and multiply it by 2. So that will give me 2N2O are turning into 2NO and 1N2. Now, since I flipped it and multiplied it by 2, I need to do the same operation to my delta H. So I will get 16.4, a positive. That's kilojoules. Okay, and then let's see. Now we can do the same thing for equation 1. I notice that there is an O2 on the product side, and that only shows up in equation 1. So we want it on the product side, so let's just flip it. Let's take equation 1 and flip it. 2NO are turning into N2 and O2. And then we got to do the same operation to our delta H, negative 179.6. Now, if we add these together, my N2s are going to add up, and then my NOs are going to cancel. The overall reaction I'm going to get is going to be 2 N2O is turning into 2N2 and 1O2. And now we can just add our delta H's. Let's see, 16.4 minus 179.6. I get negative 163.2. That's my delta H reaction per kilojoule mole. So now they want the heat released per some amount. And our delta H reaction is on a per mole reacted basis. So let's convert that 25 grams into moles. So we have 25 grams of N2O. And the molecular weight of N2O is going to be 2 times the molecular weight of nitrogen, which is 14.07, plus the molecular weight of oxygen, which is, I'm just going to call it 16. So 14 times 2 plus 16, I get a molecular weight for N2O of 44.014 grams per N2O in 1 mole of N2O. Now we need to go from moles of N2O into kilojoules. So this sort of delta H reaction is per 1 mole of overall reaction. So we need to use the stoichiometric coefficients here. Because the stoichiometric coefficient in front of my N2O is a 2, my unit conversion here is going to be 2 moles of N2O are going to get me the negative 163.2 kilojoules. I need to do 2 moles in the denominator because that's the stoichiometric coefficient in front of N2O. This negative 163 is for like 1 mole. So anyways, now if we do that, we will get, we should have kilojoules because grams N2O cancel, moles N2O cancel, we should just have kilojoules. If we do this now, 25 divided by 44.014 times negative 163.2 divided by 2, I get negative 46.35. So that looks like E. 11E. Okay. 12. Use the bond energies given below to estimate delta H for the following reaction. So let's first figure out how many reactions we have of each, and then we can do reactants minus products to find our change. So let's write that out. It's going to be the bond energy of the reactants minus the products. All right, so Actually, I'm going to omit that. Okay, so this is going to be equal to, let's do the reactants first. In this first one, this is, what does this molecule look like? It looks like, actually, we only have 4 hydrogens, which means we have a double bond. The way I just came up with that is because one carbon should have 4 bonds, and if we only have 2 hydrogens attached to each, I know there's a double bond. So this first molecule has 1 carbon-carbon double bond, which is 614, and it has 4 carbon-hydrogen single bonds. So 4 times 413. I got that from there and then there. Okay. So there, here, I'll label these 2. So this is 1, that's 1. Okay. HBr is just 1 single bond. It's a hydrogen bonded to a bromine. So that's just 363. We'll call that 2. And then let's minus our products. This molecule looks like carbon attached to carbon, like this. So in this molecule, we have, this is the product, by the way. In this molecule, we have a carbon-carbon single bond, 347. We have 5 carbon-hydrogen bonds, so 5 times 413. And then we also have a carbon-bromine bond, which is 276. Okay, so now we can simplify these. I'll do it one step at a time. So 4 times 413 plus 614. So that first molecule is 2,220 or 2,266 plus 363 minus 5 times 413 plus 276 plus 347. This one is 2,688. So now, if we sum these up, 2,266 plus 363 minus 2,688, I get negative 59 kilojoules per mole. I get 12B. Nice. 13. Might need the periodic table for this one. Okay. Which one of the following correctly lists the 3 atoms in order of increasing electronegativity? Okay. The periodic table is not syncing. Oh, there it is. Okay. 13. Which one of the following correctly lists the 3 atoms in order of increasing electronegativity? I know electronegativity on our periodic table trends this way, with fluorine being a very high electronegativity, and then the stuff in this corner being very low electronegativity. So let's find our 3 atoms and see which ones follow that trend. So AS is right below phosphorus. Oh, phosphorus, speak the devil. Okay, and then sulfur. So let me actually do these in different colors. Okay, so those are our 3 elements. Sulfur is the closest to the top right, so it's the most electronegative, and then phosphorus is a energy level above AS, so it's going to be a little bit more electronegative. So that's our arrangement. So leaves us with answer choice A. I'll give it a little bit more of an explanation too as to maybe why we know this. 13A, yeah. So AS, I think it's arsenic. I keep calling it AS. Let's compare AS to phosphorus. This is 1, 2, 3, 4. Phosphorus might only have 3 energy levels, whereas AS might have 5, actually. It might have 4 compared to phosphorus's 3. Electronegativity is the ability to attract electrons. Even though arsenic has more protons, the electrons, the outermost electrons it's attracting are much farther away than phosphorus's would be, so therefore it is a harder time attracting. Now when we compare this to, so this one is essentially phosphorus. That was arsenic. Now when we compare this to sulfur, sulfur does have the same amount of energy levels that phosphorus would have, the 3, but sulfur has one more proton, so its nucleus is just a little bit stronger, and those outermost electrons that are nearly at the same place as phosphorus's, it's going to be able to pull a little bit harder. So that's why we see the trends in electronegativity that we do. 14. What is the formal charge on nitrogen atom in nitromethane? So let's draw the structure for this. Now it's a neutral atom, so we do know the charges have to cancel out. So we have CH3, we have a methane group, and then this is going to be bonded to nitrogen, something like this, if I was guessing, where nitrogen has a +1 charge, and then oxygen has the -1 charge. So what I just drew, I kind of just did that off the dome. Well, not that I've seen this molecule before, but I know because there's no formal charge shown there, the charge has to be neutral. If I have to pick a atom to put the negative charge on, I should pick oxygen because it's the most electronegative atom, and therefore that would give me this confirmation. If you tried drawing it in another way, so for example, I could draw maybe this. I could draw this conformation where both of these oxygens have negative charges, but then the nitrogen would have a 2+, and you want to minimize these charges as much as possible because that would be less stable. So this is not our best Lewis structure. We would want 14D. 15. Which one of the following molecules or ions are linear? So let's just go through each of these answer choices. The first one, beryllium dichloride. So beryllium, it's right there. It's got a 2+ charge. And it's going to be sandwiched between 2 chlorine atoms. This has no lone pairs, so there's no other like electron dense groups on this beryllium, such as like a lone pair. So that's 180 degrees, so that's linear. So nope, nope, nope. C or E. NH2 minus. This is not in either C or E answer choice. So actually, I'll just come back to this one because this one's actually not in either of the answer choices that we know now have to be correct. So anyways, C, carbon disulfur. That was something like this. And then once again, carbon is going to form 4 bonds in the neutral state, which is when it's neutral. So once again, there's no lone pairs here. So this is just these 2 electron groups, and that's 180 degrees. So that one should be in the right answer choice, and it actually is in both answer choices. Okay, iodide dichloride. This one, I'm not even sure. Let's see, something has a positive charge on it. Let's see here. I believe it looks something like this. And then the iodide has the positive charge. So here, the problem is once again, this has 2 bonding atoms, but it actually has 4 electron regions. So in reality, this atom actually looks sort of tetrahedral. So you might have a lone pair there, you have a chlorine here, and then maybe another lone pair, then a chlorine. That's not actually how you draw a tetrahedral. So you might have like you have like a dash, like that one. That one might be coming out of the page. You might have another chlorine going into the page, and then like a lone pair. So anyways, my point is here is that it's not linear. The bond angle here is about 109 it's about 109.5 for tetrahedral style atoms. So this should not be in our answer choice, leaving us with C, which is correct. Let me also do NH2 real quick. nitrogens bonded to 2 hydrogens, which are just single bonds, and then it's just got 2 lone pairs. So once again, that's sort of that tetrahedral electron grouping, where it's got the 4 bonding regions. So same deal as this down there. 16. The trend in boiling point listed below is best explained by the boiling point is the ability of the liquid to boil off into a vapor. And when things are in the liquid phase, they are held together in large part by intermolecular forces. So we're looking for differences in intermolecular forces. Intermolecular forces increase as you increase electronegativity or types of bonding. So the different types of intermolecular forces are our main options. All molecules experience some form of London dispersion forces, which are the weakest. You can also have dipole-dipole interactions, which is where if you have 2 very polar molecules, their sort of partial positive and partial negative charges can form very stronger versions of LDFs. And then you can also have hydrogen bonding, which in our case, we do not have hydrogen bonding in any of our choices because we don't really have any very electronegative atoms. So here the trends are going to be explained mostly by these two, mostly this one. So we're essentially we're looking for an increased electronegativity or polarizability. So anyways, if the boiling point is higher, that means you have more forces to overcome. You need more energy to overcome your intermolecular forces, which means as you trend this way, electronegativity would increase. And so would polarizability. Okay. Okay, so A is not true. That's the opposite. It increases. B, increasing diameter of the central atom in the series. That's not really all that relevant what we're looking at here. Increasing polarizability, that's true. That's one of the points we said. It's similar to electronegativity. D, increasing strength of the bond to the hydrogen atoms in the series. Once again, we don't really care about the intramolecular bonding. We're just concerned with the intermolecular forces. So, and then E says increasing atomic number, positive charge on the nucleus on the central atom. Now, my thing here is answer choice B and E are somewhat functions of electronegativity, but they don't explicitly say it. So C is going to be our best choice since they explicitly say increasing polarizability. So anyways, 16C. Problem 17. List the following compounds in order of increasing vapor pressure at room temperature. So we know that vapor pressure is going to be, I'll call it P star, is going to be correlated somehow to the intermolecular forces. So this question is essentially asking us, can we identify the relative intermolecular forces of the compounds and know the relationship between vapor pressure and intermolecular forces? And the relationship between these two is that as intermolecular forces increase, vapor pressure is going to decrease. I know Khan Academy has done videos on more conceptual understandings of vapor pressure, and those are probably going to be better than what I can explain. But a real quick one, if you have high intermolecular forces, you're going to be more, it's going to be harder to boil off, and you're going to have more liquid, and that might preferentially reduce your vapor pressure because you have less vapor. That'd be contributing pressure to your liquid. So anyways, that's just one quick conceptual explanation. Just remember this trend: as intermolecular forces increase, vapor pressure is going to decrease. So now let's look at our species and identify relative intermolecular forces. So the first thing I notice is that these two compounds both have hydrogen bonding, but the second one has 2 OH groups, so that means this one is probably going to have our highest intermolecular forces. I know hydrogen bonding is the strongest type of intermolecular force we can have, So if we have two groups that can contribute to hydrogen bonding, that's going to be really very high intermolecular forces. It's going to be higher than just one. And then this species has no hydrogen bonding. So this one's probably going to be 3 and then 2. So if this species has the highest intermolecular forces, it has the lowest vapor pressure, which leaves us with C and D, and then this species would be second, which leaves us with 17E. 18. Which one of the following compounds would you expect to exhibit only London dispersion forces in a pure sample? So the 3 types of intermolecular forces that we look at, we have London dispersion forces, which every species exhibit. Each species, different compounds might have different levels of London dispersion forces, but London dispersion forces are the weakest and they exist in every compound. And they arise just from like random dipoles between molecules that can sort of form between like very small partial positives and negatives. We also have dipole intermolecular bonding. This arises from very polar molecules where, so say I had something like this. This fluorine right here might be very partially negative, and this hydrogen might be partially positive. If I had 2 of them, if I had another compound, like of the same one, this partially positive hydrogen might form a bond with the partially negative fluorine. So that's dipole-dipole bonding. You get that from polar molecules. And then we also have hydrogen bonding, which is just a special form of dipole-dipole intermolecular bonding. So anyways, we're just looking for a case in this problem. We're looking for one that only has LDFs and not either of those 2. So first answer choice, carbon tetrachloride. This molecule is symmetric, which means it's not polar, so this one's probably going to be our answer choice. Let's check out the rest of them, just to be sure. Yeah, so if we look at answer choice B, methyl chloride, this one is a very polar molecule, and you're going to get some of those. Dipole-dipole bonding. So not B, phosphorus, CO1. Okay. Phosphorus trichloride looks something like this. Here we're going to have a lone pair, which is extremely partially negative. There we go. And then our phosphorus probably is partial positive charge. And you're going to get dipole-dipole bonding there. Is it worth going through the rest of these? Yeah, we can keep going. Same deal. Dichloromethane is very similar to B. I mean, I'll write it out just because, but pretty much the exact same reasoning for this molecule. Why this one would be polar. So it's not D. E, the cis isomer of, let's see, what is this? This molecule. In case you don't know what cis is, I just drew the cis. I just drew the cis conformation of this. The trans would be this instead. So when we say cis and trans, it's saying which side of the group's on. So if they're cis, that means the chlorines are on the same side, or like the heavier groups are on the same side, as opposed to trans, where they'd be opposite from each other. And this one, we have a double bond, which is usually very polar. Same with very polar groups, and it's asymmetric. So it's not E. 18A. 19. Allene is a hydrocarbon with the formula of that. Predict the hybridization around the central carbon atom, the shape around the terminal carbon atoms, and the bond between the 2 methyl groups. Okay. First, let's draw out what this looks like. So we got 3 carbons. There's double bonds in between them. And then there's 2 hydrogens coming off each of them. Now I know from valence bond theory that these hydrogen groups are actually going to be offset. And if you got this problem wrong, I'm guessing that's why, because you didn't recognize this. Because instead, I'm assuming most people would write this initially as this molecule. Oops. But these hydrogens are going to repel each other, and they're going to want to be offset by 90 degrees because that would be less electron repulsion. This one's a little bit hard to picture in your head, but just imagine those hydrogens are going to be on a plane. These hydrogens might be on a plane kind of going into the page, and then these ones might be on a plane like parallel with the page. Kind of really hard to describe on 2D with an iPad. But this is our model where the hydrogens are going to be offset. So anyways, now let's get into answering the problem. All right, first of all, hybridization around the central carbon atom. The central carbon atom has 2 bonds. So I know it is sp hybridized. You add like 1 p every time you add another bond. So if this carbon instead had like 3 bonds, like say it had some, if I had a carbon like this would be sp2 hybridized. And if I had CH4, it'd be like sp3 hybridized. But in our case, we only have 2 bonds, so it's sp hybridized. So it's not DRE. How about the shape around the terminal carbon atoms? These carbon atoms have 3 bonds, so I know they are trigonal planar. So it's not A. And let's see, angle between CH2 groups. We talked about this earlier. They're going to be offset by 90 degrees as opposed to being on the same plane. So it's not B. We get 19C. 20. Acetone has the formula that, which one of the following is true? Let me draw acetone real quick, just so we have it. Okay, that's kind of what acetone looks like. A, the carbon-carbon bonds in acetone are formed via the overlap of an sp3 hybrid orbital on a terminal carbon atom with an sp2 hybrid orbital on the central atom. That is true. These are sp3 hybridized because they have 4 bonds. This one's sp2 hybridized. Anyways, let's read the rest of the choices. B, there's no free rotation around carbon-carbon bonds because the central C atom is sp2 hybridized. This is not true. You're only going to get not rotation around bonds if it's a double bond. So if I had something like this. Okay, this is, wow, that was really messy. But anyways, these can't like rotate around this bond. But if I just have single bonds can rotate instead. So, you know, if I had another carbon coming off this, even though that one double bond can't rotate, it doesn't mean that this can't like rotate around that bond. So just being adjacent to a double bond does not make you immune from rotating. So B, false. C, more than one equally valid resonance structure can be drawn for acetone. The only resonance structure I could see was if you wanted to move the electrons up there, and instead you got a positively charged carbon and negatively charged oxygen in that. And that's not equally valid because you're putting charges on atoms, which is not as favorable. Even though the real acetone exists somewhere between these two resonance structures, this one would be our favorite. So C is wrong. D, there are 2 possible geometric isomers of acetone. I just don't see how you could draw that. That's false. The entire acetone molecule is planar. Both of the carbons on the ends are tetrahedral. So if we were to actually draw in like the geometry of these hydrogens, they wouldn't just be lines. One of them might be going out of the page, and one of them might be going into the page. Because we know tetrahedral structures exist in all three dimensions, so it's not planar. 20A. 21. Which one of the following correctly describes the orbital hybridization at the indicated atoms in the structure of the nitrogenous base guanine shown below? Atom 1, I see 3 bonds, so we'll do this. Wait, oops. Yeah, we'll do this. The first atom has sp2 hybridization. This N has, once again, 3 bonds. Therefore, it has sp2 hybridization. And this N only has 2 bonds. So it is just sp hybridized. Important. So let's actually pick our answer choice first before I make a mention of something. Nope, 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 nope. (21) Which of the following correctly describes the orbital hybridization at the indicated atoms in the structure of the nitrogenous base guanine shown below? Okay. So in order to figure out a hybridization of a given atom, we need to know how many bonds it's forming with different atoms and then how many lone pairs it has. So let's start with atom 1. It's a carbon with a double bond up to an oxygen up top, and then it has a bond to some other carbon, and then a bond to, well, actually that's a nitrogen. And it has 1, 2, 3 different bonds to atoms, and it has 0 lone pairs. So therefore, if it has 3 of those regions, I know this is going to be sp2 hybridized. Okay, let's look at atom 2. I'll do it in blue. Okay, atom 2 is this nitrogen that has a bond off to some carbon, a hydrogen there, and maybe another hydrogen, and then it also has a lone pair. I know nitrogen is going to carry a lone pair with it if it's neutrally charged. So let's count these up. It is 1 bond to the carbon, 2 to the hydrogen, 3 to the hydrogen, and then we're also going to count the lone pair. So this is sp3 hybridized. Let's take a look at our last one, this nitrogen. This nitrogen has a double bond up to a carbon, a bond up to another carbon, and then a lone pair. 1, 2, 3. Therefore, this atom is sp2 hybridized. So let's pick our answer choice, and then I'll maybe generalize this for more problems to make it more clear. That's going to leave us with answer choice B. So anyways, like I was saying, when you're figuring out hybridization around an atom, you're going to want to count the number of atoms it has a bond to, and then add on the lone pairs. And then if it has two of those, you'd be sp hybridized. If it has 3, you'd be sp2 hybridized, and then 4, you're going to get full sp3 hybridization. So that's just a quick high-level overview on how you get the hybridization of an atom. So 21b. 22. Given the condensed structure of the molecule penguin shown below, how many sigma bonds are present? So a sigma bond is a single bond, and a pi bond is usually the double, not usually, it's the double bond. So like that's a pi bond, that's a pi bond, that's a pi bond. Everything else would be sigma bonds. Okay. They want to know how many sigma bonds are present. So one of the things here is we're going to need to write in implied hydrogens. So when we write in this line structure, like organic molecules, we don't write in hydrogens because they're implied. Just to make it simpler, we don't write in hydrogens. So I know a neutrally charged carbon is always going to have 4 bonds, whether it's something like this, or if the carbon is a double bond, maybe it only have 2. It's going to form 4 bonds every single time, no matter what, if it's neutrally charged. So I can now go around this molecule and write in all the implied hydrogens. There's 1 there. There are 3 here. There's actually 3 on all of these. There's going to be also 1 there. There is not one here because that carbon already has 4 bonds. Yeah, so this one already has 4 bonds, this one already has 4 bonds, that one already has 4 bonds. Now let's just go up and count all these sigma bonds up. I'm going to do the non-hydrogens first, and then we'll just add in the hydrogens. So, actually, it just glitched me all the way to the top. All right, we've got 6 in the ring. Those are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we have 11 non-hydrogen bonds, and then the hydrogen contribution is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 25. If I add those up, I get 25. 22D. So the trick here is being able to write in implied hydrogens onto an organic molecule. And you need to know that carbons form 4 bonds. And also that a sigma bond is a single bond and a pi bond is a double bond. Problem 23. How many possible isomers exist for C4H8, including cyclic compounds? So, first of all, let's figure out how many unsaturations we have in this molecule. So when I say unsaturations, I'm referring to either a double bond or that's supposed to be an arrow, or a cyclic feature. In case you're not familiar with saturation of organic compounds, say we use something like this. This would be ethane, and if it has no double bonds, this is what we would call fully saturated, where each carbon has the maximum number of hydrogens that it could possibly have. So the end carbons have 3, and then the interior carbons would have 2. And this is what we call fully saturated. Now we could have an unsaturated compound where if we took off, imagine we took off 2 of these hydrogens, we would need to now introduce a double bond there to make it electrically possible. We need to introduce that double bond, and then we would call that an unsaturation. We could also, so now this has 8 hydrogens. We could also do something like this, where we now have a cyclic structure, but we don't need the double bond, and we still get 8 hydrogens. So let's figure out how many unsaturations we have first. The amount of hydrogens we would expect to have in a fully saturated molecule is 2n plus 2, where n is the number of carbons. So for us, we have 4 carbons, so that would be 8 plus 2. So we would expect to have 10 hydrogens. We only have 8 hydrogens, which means we're sort of missing 2. And if you take away 2 hydrogens, that's equivalent to like 1 unsaturation. Also, equivalently, you can kind of just draw the molecule. So we know we have 4 carbons. If you only draw 8 hydrogens on here, you can just kind of count how many unsaturations you're going to need. So I just drew 8 hydrogens. And I can tell that I'm going to need a double bond here in order to make everything neutrally charged. So that's another way, perhaps a less quantitative way to tell how many unsaturations you're going to need. So we know we need 1 unsaturation here. So now let's go through and just try to draw as many isomers as we can. So if it's purely linear, this is my ethane structure, and we know we have 1 unsaturation. So we could have the unsaturation there. We could also have the unsaturation on this bond, or on that bond. Now, we notice this is the cis isomer, and we could have those 2 methane groups alternatively going the other direction, like this. Let me draw like this instead, actually. Oops. So this would be the, wait, this is the trans isomer. Sorry, I apologize. This is the trans isomer. This would be the cis isomer. Cis and trans refers to the direction the heavy groups are pointing in across the double bond. So my 2 methane groups in the trans isomer are pointing in opposite directions. And then in this, wow, I keep drawing it wrong. Okay, in cis, they point the same direction. Sorry. Cis means they're on the same side, trans means they're on the opposite side. Sorry. On the cis conformation, they're on the same side, and then trans, they're opposite. Okay. That's all the ones we can do for that linear arrangement of the carbons, we could also do something like that has 4 carbons, and we could put the double bond on one of those. If we tried to draw this, that's actually the same molecule, just rotated 90 degrees. So there's 4 answer choices. Now, those are our 4 answer choices without introducing a cyclic feature. So now let's try to draw some of the cyclic compounds. We have 4 carbons. We could put them in a square that's got 8 hydrogens. And let me just prove to you that this is equivalent, because this structure is going to have 8 carbons, or 8 hydrogens. We could also do a triangle with 1 carbon going off to the side. And let's see, we could not do a cyclic structure with less than 3 carbons, because that would just be a 2 carbon like double bond or a single bond. So looks like these are all our answer choices. 1, 2, 3, 4, 5, 6, which leaves us with 23C. Okay, nice. 24. Which one of the following functional groups is not in tyrosine? All right, let's see here. Well, actually, let's just go through tyrosine left to right and identify what we see. This is a carboxylic acid. You have a double bonded oxygen with the OH coming off the side. We call that a carboxylic acid. An amine group. That's what we call an amine. Also, if you don't know what R means, that just means going off into like the organic part, like some carbon chain. Okay, let's keep going. And then we have an alcohol. So ROH is an alcohol. Let me label these actually. Carboxylic acid, amine, alcohol. Okay. We also have a benzene ring in the middle. Okay, so which one of these is not? We found an amine, we found a carboxylic acid, and we found an alcohol. So our answer choice is D. What does an aldehyde look like? An aldehyde is this functional group, where it's similar to a carboxylic acid, but instead of a hydroxide, you're going to have just an H. So 24D. Polypropylene is a polymer derived from the monomer propene. What is the degree of polymerization for a single chain of polypropylene with a molecular weight of that much? So let's find the molecular weight of one repeating link. So it looks like this is our monomer. Okay, let's find the molecular weight of this. So we have 3 carbons. We have 6 hydrogens. So the molecular weight of this is going to be 3 times 12.01 plus 6 times 1.007. Throw that in the TI-84. And my calculator's dead. Just kidding. Throw it in the iPhone. Okay. 3 times 12.01 plus 6.042. I'm going to get 42.072. And then we can just take our 21,500 and divide it by the molecular weight of one of our links. So 42.072. 21,500 divided by 42.072 gets me 511, which is pretty close to E. So here's the problem. You just got to identify what is the repeating unit. For us, it is simply just those two. And then you can find the molecular weight of that and divide the overall molecular weight divided by your one repeating unit. And we get 25E. Problem 26. Cross-linking of polyvinyl alcohol with borax results from which intermolecular force? I see alcohol, which is already screaming hydrogen bonding. Hydrogen bonding is the strongest type of intermolecular force we study. So if you see alcohol, that means OH, and we know it's going to exhibit hydrogen bonding. So 26A. 27. Infrared spectroscopy can be used to study carbon-carbon and carbon-oxygen bonding. If nu is the symbol for the frequency of stretching vibration, which of the following pairs of statements are correct? Okay. So looks like we're comparing like the frequency of triple bonds to double bonds to single bonds for the same atom, except for B. Okay, so what we need to know here, let's compare a carbon-carbon double bond to a single bond. This double bond is going to have a lot more electron density, and it's a much stronger bond, which means it's going to have a higher frequency. It's going to have a higher nu. And the weaker bond is going to have a lower frequency. So that leaves us, and that applies, it's going to be the same thing for the carbon-oxygen bonds. So that leaves us with B or C. These two, for my IR spectra, those two both exist in the 1600 wave number region. And these two are both in the fingerprint region. So B could be true, maybe in theory, but in all the chem classes we've seen, we don't really study the fingerprint region, so I'm suspect that this is actually true. But regardless, C is definitely true, so we're going to go with C here. Yeah, we're going to go with C, because that is undoubtedly true, and that's our best answer choice. Also, I believe the carbonyl bond has a slightly wider range than the alkene bond. So, anyways, regardless, C is definitely our best answer choice there. So, 27C. 28. Maltose is a disaccharide formed from 2 glucose units. The balance reaction for maltose formation from glucose is shown below. Which of the following statements is correct? Okay, so they want to figure out, is it an addition reaction or a condensation reaction? And then they want to know the hybridization of the oxygen. So first of all, if we're ejecting a water like this, it's definitely going to be a condensation reaction. A addition reaction would be if a water was not given off like this. So this is just kind of knowledge of what an addition or condensation reaction might be. An addition might be something where, say we have like a carbonyl, and we had like a ether, and this was like negatively charged, and that was doing like I don't know if this is actually worth showing, but if we had some reaction where we didn't give off some extra product like water, then that could be an example of an addition reaction. But here we have water as a product, so it's going to be condensation. Okay, and now they want the hybridization of the oxygen. So they want the hybridization of that molecule. And we have, let's see, this oxygen it's got going up to the R group. Above it, it's got a bond to the hydrogen, and then it's got 2 lone pairs. 4 bonding groups mean we are sp3 hybridized. So that leaves us with, what is that, 28E. 29. The intermolecular forces that bind 2 nucleic acid strands in a DNA double helix primarily consist of hydrogen bonds between the nuclide bases. Oh, actually, there's also D. So I know it's hydrogen bonds. This one's also just a specific knowledge question, but we know it's hydrogen bonds, and they are between the nucleotide bases. So that's going to leave us with the answer choice A. This one's hard for me to explain, so if you just look up like the DNA double helix structure, you can fact check that this is true. You can see like the diagrams of the hydrogen bonding holding it together.